Yeah, okay, so thank you very much. And so first of all, so I'd like to thank to the organizer for inviting me to such an exciting conference. And so I'm SEKI from University of Tokyo, and today I'd like to talk about the novel materials with the magnetic skyrmions and their three-dimensional dynamics. And so today I'd like to mainly discuss about this magnetic skyrmion, which represents this kind of swirling spin texture, as already introduced by many other previous speakers. And so when we look at this kind of the vortex object from the top view, then sometimes it looks like a particle. And when we look at this vortex object from the side view, then sometimes it looks like a string. And so today I'd like to discuss what kind of the function can be expected from such as a magnetic vortices. And so as already introduced, so the magnetic skyrmion appears as this kind of the vortex like the swirling spin texture. And in the real material, its typical diameter is 1 to 100 nanometer. And it is characterized by so-called the skyrmion number, which means that the rearrangement of the spins within a single skyrmion can wrap a sphere just one time. And so this is a topologically stable object with a particle-like character. And because of such as a stable particle nature and nanometric scale, so the skyrmions are now intensively studied as a potential candidate of the new information carrier for magnetic as a storage device. And so one unique feature of such skyrmion is that, so especially in a metallic system, so the skyrmion can be driven by the electric as a current. And so by using this kind of the feature, so several different types of the skyrmion-based memory or logic gate device has been proposed. And in such a system, so the presence and absence of the skyrmion at some specific position is considered as information 0 or 1. And so with such a manner, so the skyrmion particle is now intensively studied as a candidate of the information bit. And so today I'd like to mainly discuss about the two different topics about this as a magnetic as a skyrmion. And so in the first half, I'd like to introduce our recent material development, in particular the discovery of the nanometric skyrmions in a central symmetric system. And in the second half, I'd like to talk about the skyrmion string in a three-dimensional system. And so let's start from the first topic about the material development. And so originally, the magnetic skyrmions are discovered in a series of the non-central symmetric system. And so in such a non-central symmetric environment, so usually its magnetic Hamiltonian is described by these two terms, and each term corresponds to the exchange and Jaroszynski-Murier interaction. And because of the competition between these two terms, so this kind of the swirling as a skyrmion spin texture can be stabilized. And actually, most of the previously reported skyrmion hosting materials are characterized by such as a non-central symmetric crystal structure. And in this case, the skyrmion diameter is determined by the ratio between J and D. And so typically, 10 to 100 nanometer diameter of the skyrmion can be realized in a bulk as a system. And however, if we consider this skyrmion as an information carrier, then to enhance its information density, so the realization of the smaller size of the skyrmion is very important. And so from the viewpoint of the material development, so it is very important to understand whether we can realize even smaller size of the skyrmion in a central symmetric system or not. And according to recent theoretical studies, so actually this is predicted to be possible. And so here one important breakthrough is the recent discovery of the novel skyrmion formation mechanism mediated by the itinerant electrons. And so in this new theoretical framework, so we assume the coexistence of the localized magnetic moment and the itinerant electrons. And in such a situation, so its magnetic Hamiltonian can be mainly described by these two terms. And the first term corresponds to the conventional two-spin RKKY interaction, and the second term corresponds to the higher order four-spin interaction. And if such kind of the situation is realized under the highly symmetric crystal lattice, such as the tetragonal or hexagonal lattice system, then the interference of the multiple number of the equivalent nesting vector lead to the stabilization of the skyrmion crystal state. And one unique advantage of this new mechanism is that, so in this case, the skyrmion can be stabilized even in a central symmetric system. And also, in this case, the skyrmion diameter is determined by the nesting vector. So typically, a few nanometer diameter. So extremely small size of the skyrmion can be ubiquitously realized. And the theory predicts that to realize such kind of the situation, so the employment of the rare intermetallic alloys with highly symmetric crystal lattice will be promising. And following this new strategies. So recently, several gadolinium-based centrosymmetric skyrmion hosting materials are discovered. And so these compounds commonly contain the gadolinium 3+ ion with a highly symmetric crystal lattice. And these compounds commonly host the extremely small size of the skyrmion. And in such systems, so the symmetry of the underlying crystal structure essentially affects the ordering manner of the skyrmion. And so in case of the, for example, hexagonal crystal structured system, the skyrmion forms the triangular lattice. And on the other hand, in case of the tetragonal crystal structured system, the skyrmion forms the square lattice. And in particular, this tetragonal gadolinium ruthenium 2 silicon 2 compound was found to host the smallest size of the skyrmion ever reported for the single component as a compound. And so from now on, I'd like to focus on this as a tetragonal gadolinium ruthenium 2 silicon 2 as a system. And so this is a crystal structure of this gadolinium ruthenium 2 silicon 2. And so basically each ion independently forms a square lattice and they just stacked along the 0, 0, 1 direction. And so it is very simple centrosymmetric tetragonal crystal structure. And the magnetism is governed by the gadolinium 3+ ion with the Heisenberg type as a magnetic moment. And this is a typical temperature magnetic field phase diagram. And so by applying the out-of-plane direction of the external magnetic field, we can stabilize the square lattice of the skyrmion. And this is corresponding the real space as a spin texture obtained by the Lorentz transmission electron microscopy as a technique. And so this is experimental data. And so you can see that some swirling as a skyrmion spin texture forms a beautiful as a square lattice. And here the diameter of the skyrmion is as small as 1.9 nanometer. And so this is the smallest as a size of the skyrmion ever reported for the single component as a bulk as a material system. And so for this as a gadolinium ruthenium 2 silicon 2, so the emergence of the extremely small size of the skyrmion is now established. And one unique feature of this compound is that so this crystal structure allows a quite wide variety of the chemical as a substitution. And so actually many family compounds with the same as a crystal structure are also found to host a similar skyrmion spin texture. And so this is the temperature magnetic field phase diagram for each as a compound. And so in case of the original gadolinium ruthenium 2 silicon 2, so this compound hosts only a single skyrmion crystal state. And on the other hand, in these family compounds, there appears a multiple number of the skyrmion crystal states. And so from now on, I'd like to focus on this germanium substituted compound as an example. And so basically this germanium substituted compound has exactly the same crystal structure as its silicon counterpart. And when we look at its magnetic field dependence of the hole resistivity, then we can identify the emergence of some two prominent peak structure in the hole resistivity as a profile. And so it can be ascribed to the so-called topological hole effect as originating from the skyrmionic spin texture. And next, to identify the detailed magnetic structure in each phase, so we perform the intensive resonant X-ray scattering experiment. And so today I skip the detail, but our final conclusion is that so in this compound, by applying the out-of-plane direction of the external magnetic field, so quite rich variety of the topological magnetic transition can be observed. And so in the zero field as a ground state, so this compound hosts a screw type as a helical magnetic order. And by increasing the amplitude of the out-of-plane direction of the external magnetic field, then the local spin swirling manner was partly this as a screw stripe was first pinched off, and then it turns into the elliptic skyrmion. And by further increasing the field amplitude, then the local spin swirling manner was partly flipped, and it turns into the so-called melon anti-melon pair. And by further increasing the field, once again, the spin swirling manner was flipped, and it turns into the circular skyrmion. And by further increasing the field, finally, core magnetization direction was flipped, and it turns into the vortex. And so with such a manner, so by applying the out-of-plane direction of the external magnetic field, so this compound shows a multiple step as a topological transition among the skyrmion and melon crystal states. And so to briefly summarize this part, so the previously magnetic skyrmions observed in non-central symmetric system with Jaroshinsky-Morier interaction. And in this case, typically 10 to 100 nanometer diameter of the skyrmion can be realized. And on the other hand, recently some novel skyrmion formation mechanism mediated by the itinerant electron has been proposed. And in this case, so realization of the 1 order of magnitude smaller skyrmion size has been predicted. And actually, following this new strategy, so we discovered the extremely small size of the skyrmion or a very rich variety of the topological magnetic quartz particles. And so these findings strongly suggest that this novel skyrmion formation mechanism works quite well. And so further material development following this new strategy will lead to the further discovery of the even smaller size of the skyrmion or a richer variety of the topological magnetic quartz particle. And so far, as I mainly discussed the RKKY-induced multiple Q state in a 4F electron system. And then next important question is whether similar mechanism also work in a 3D electron system or not. And so to discuss this point, I'd like to introduce this cobalt-tantal sulfur system, which was recently found to host a triple Q non-coplanar antiferromagnetic order. And so this cobalt-tantal sulfur compound was originally discovered by the Professor Stuart Parkin more than 40 years ago. And recently, so it is classified as a member of the so-called intercalated van der Waals materials. And so this is the crystal structure of this system. And so basically, cobalt magnetic ion was intercalated at the van der Waals gap of the two-dimensional tantal S2. And this crystal structure is characterized by space group P6322. So it means that this is a chiral hexagonal crystal structure system. And so this is the temperature dependence of the magnetic susceptibility and spontaneous magnetization. And so this compound shows the antiferromagnetic order below 36 Kelvin and below 24 Kelvin, as how we can identify the emergence of the very tiny spontaneous magnetization along the 001 direction. And so it strongly suggests the realization of some time reversal symmetry broken antiferromagnetic order. And this is the corresponding magnetic field dependence of the magnetization, longitudinal resistivity, and Hall resistivity. And when we look at this as a magnetization, then we can identify the tiny hysteresis loop in the low field region, and it is consistent with the emergence of the tiny spontaneous magnetization. And at around 4.5 Tesla, there appears another metamagnetic transition. And when we look at the corresponding Hall resistivity profile, then we can see that this compound's Hall resistivity is not proportional to the magnetization at all. And at zero field ground state, so this compound shows a giant spontaneous Hall effect, and its Hall angle is as large as 2%. And so this is almost comparable with the typical ferromagnetic system. And so the emergence of such giant spontaneous Hall effect strongly suggests the realization of some time reversal symmetry broken antiferromagnetic order. And next, to investigate their magnetic structure, so we perform the detailed magnetic structure analysis based on the polarized neutron scattering experiment. And today, I skipped the detail, but our conclusion is that so in this compound, this kind of the all-in, all-out type non-coplanar antiferromagnetic order is realized. And this magnetic structure is characterized by the magnetic point group as a 3,2-, and it breaks the time reversal symmetry. And the corresponding shape of the electrical conductivity tensor is like this. And so this magnetic symmetry allows the emergence of the non-zero off-diagonal component in the conductivity tensor. And so it suggests the emergence of the fictitious magnetic field along the 001 direction. And it is very consistent with the experimentally observed selection rule of the spontaneous as a Hall effect. And in general, when the conduction electron pass through this kind of the non-coplanar spin texture, then they are expected to feel a giant fictitious magnetic field originating from the additional Berry phase contribution. And this phenomenon is often called the topological Hall effect. And so the presently observed giant spontaneous Hall effect in this compound can be well understood within the framework of such as a topological Hall effect. And so for this cobalt-tantal sulfur system, so the realization of such all-in, all-out type non-coplanar antiferromagnetic order is now established. And recently, Christian Batista and his collaborator also independently reported the same magnetic structure for this compound. And they also performed the additional ALPS measurement to identify the Fermi surface shape. And their conclusion is that so this triple Q antiferromagnetic order is stabilized by the RKKY-driven mechanism associated with the three equivalent nesting vectors. And so this finding strongly suggests that such RKKY-driven mechanism also works well in a 3D electron system. And so further search of the similar RKKY-driven multiple Q spin order in both 4F and 3D electron system would be a very interesting direction for the future material development. Okay, so this is the first half about the material development. And then let's move on to the second topic about the skyrmion string in a three-dimensional system. And so, as already discussed, so in the two-dimensional system, so skyrmion has the character of the particle, and so it is now intensively studied as the candidate of the information bit. And on the other hand, in the real three-dimensional system, so skyrmion is expected to have a character of the string. And this skyrmion string usually consists of the uniform stacking of the two-dimensional skyrmion along the string direction. And we naively expect that this skyrmion string may be utilized as an information transmission line. And however, in the previous experiment, so direct visualization of the three-dimensional shape of the skyrmion string has not been achieved. And this is mainly because so it is well known that the direct visualization of the three-dimensional spin texture is very difficult. And so in the traditional approach, magnetic skyrmions are observed by using this Lorentz transmission electron microscopy technique. And in this case, the skyrmion particle is identified as this kind of the particle-like pattern. But this corresponds to the situation like this. So in this case, the skyrmion string is observed only from the one specific direction. And so in this case, the information along the depth direction was averaged out. So only the two-dimensional information can be obtained. And to overcome this problem, so the one naive solution is that, so for example, by observing the target object from the various different angles, then we should be able to obtain the three-dimensional information. And so one promising experimental approach to realize such kind of the concept is the so-called X-ray magnetic tomography technique. And so this tomography technique is frequently used for the CT scan of the human body. And so later in this conference, so there will be a much more detailed explanation about this measurement technique. But basically, so in this technique, so the two-dimensional transmission images are taken from various different angles. Then we can reconstruct the three-dimensional distribution of the local magnetization. And so recently, we attempted to apply this X-ray magnetic tomography technique for the direct visualization of the three-dimensional shape of the skyrmion string. And so this here, our target compound is famous as a room temperature skyrmion hosting as a Heusler compound. And so now we are showing some reconstructed three-dimensional distribution of the 001 component of the magnetization. And so now sample is rotated, and you can see that some tube-like object is clearly running through the entire thickness of the sample. And so it represents the skyrmion strings. And to better understand these data, so I plotted several cross-sectional images here. And so the left panel represents the top view XMCD transmission image. And so in this case, the skyrmion string was observed from the tube direction. So each particle-like pattern represents the individual skyrmion. And when we cut the sample at this plane A, then the corresponding cross-sectional image is like this. And so you can identify some tube-like object, and it represents the straight skyrmion string. And on the other hand, when we cut the sample at this plane B, then the cross-sectional image is like this. And so in this case, you can identify some interrupted or Y-shaped skyrmion strings. And so by using this kind of X-ray magnetic tomography technique, we can directly visualize the three-dimensional shape of the skyrmion strings or their defect structures. And once such string-like object is identified, next important question is what kind of function can be expected from such the string-like object. And so naively thinking, so when we make some vibration on a string, then this vibration should propagate through the string path. And so maybe skyrmion string can be utilized as an information signal transmission line. And however, as before discussing the possibility of such potential application, so it is very important to understand the fundamental propagation character of the excitation mode on the skyrmion strings. And theoretically, so such skyrmion strings are expected to host three distinctive propagating excitation mode. And so here I visualize the situation where the local skyrmion excitation is launched at some selected plane, and this vibration propagates along the plus k and minus k direction on a string. And so basically, we can expect the emergence of the three distinctive propagating excitation mode, namely the counterclockwise, bridging, and clockwise as excitation mode, as shown here. And then next important question is how can we experimentally evaluate their propagation character? And so for this purpose, we employ the measurement technique so-called the propagating spin wave spectroscopy. And so this is a typical device structure for this kind of the measurement. And so first, we fabricate a pair of the coplanar waveguide antenna on the silicon substrate, and then put miniature-sized single crystal of the skyrmion hosting material on top of that. And first, we inject the oscillating electric current into the one of the waveguide, and then it generates the oscillating magnetic field. And this induces the oscillation of the skyrmion string. And then this skyrmion string vibration propagates through the sample, and when it reaches to another antenna, then it inversely induces the oscillating electric voltage. And so by performing the measurement of the mutual inductance between port 1 and port 2, we can directly evaluate the propagation character of such excitation mode on the skyrmion strings. And so this is experimentally observed as a propagation character of the excitation mode on the skyrmion strings. And so here I plotted the mutual inductance spectra for several different frequency range. And so from this data, we can identify the emergence of the three distinctive excitation mode. And from the comparison between theory, we can assign each mode as a counterclockwise, bridging, and clockwise as excitation mode. And another unique feature is that in this data, the red and blue colored data represents the propagation along the plus k and minus k direction. And so this data indicates that propagation along the plus k and minus k direction is not equivalent. And so this skyrmion string excitation shows some kind of the non-reciprocal as a propagation character. And such emergence of the non-reciprocal propagation character can be well understood by considering its dispersion relationship. And so this is a theoretically calculated as a dispersion relationship for the skyrmion string as excitation. And so actually we can identify the emergence of some mode-dependent as asymmetric as dispersion. And so the experimentally observed as some mode-dependent as a non-reciprocal propagation character can be well understood by considering such mode-dependent asymmetric as a dispersion relation. And another important information about this skyrmion string excitation is that by analyzing this data, we can estimate the decay length of this as a propagation mode. And actually, we can confirm that its decay length is more than 1,000 times longer than the skyrmion string diameter. So this oscillation mode can propagate through the very long distance. And so such kind of the future implies that maybe skyrmion string can be utilized as an information transmission line. And so because of its topological protection, such skyrmion strings are expected to be robust and flexible. And also the presently observed as excitation modes are expected to propagate through the string path, even for the curved manner of the skyrmion string. And so such kind of future implies that maybe skyrmion string satisfy some ideal condition for the information transmission line. And so for the future direction of the study, for example, further consideration of the network structure of the skyrmion string maybe interesting as a direction. Okay, so today I mainly talked about the two different topics. So in the first half, I talked about this material development, and especially the nanometric skyrmions in the central symmetric system. And in the second half, I talked about the visualization and the excitation of the such skyrmion string. So these results imply that maybe magnetic skyrmion particle and string can be unique information media for novel spintonic device. And so further investigation of such topological spin texture would be very interesting. And finally, so this work has been performed in collaboration with many people. And so I'd like to thank to the collaborators once again. So thank you very much for listening. Thank you.